high energy level. Now, this electron is now said to be an excited. Once the electron has jumped from a lower level to a higher level, the atom is said to be excited. It is no longer normal. In a normal atom, you will find the electron in the ground state. Remember, we're talking about hydrogen atom. In a normal hydrogen atom, the electron will be in the ground state. The moment that electron has received extra energy and moved into an outer orbit, we say the atom is excited. Now, an atom or an electron cannot stay excited for a long time. It has to come back to normalcy. Now, how do an excited electron come back to its normal state? An excited electron has extra energy. If it has to come back to normalcy, it has to throw away the extra energy. Now, this is the mechanism of radiation. Now, this electron returns to one of the lower levels by throwing away the extra energy in the form of photons. In other words, light is made up of photons. Photons are these packets of energy. The packets of energy that is electrons, the excited electrons, throw away when these electrons jump from a higher excited state to lower levels. And that's very important. Now, look at this one here. An electron in the excited state n equal to 3, this is n equal to 3, has an energy E3. Here, electron has the energy E1. In the second state, it has an energy E2, E3, and so on. Now, if this electron, which has an energy E3, jumps to n equal to 2, so from the level n equal to 3, if an electron jumps to n equal to 2, that means an electron here has an energy E3. If it comes here, it can only have an energy E2. So if it jumps from n equal to 3 to n equal to 2, it has to radiate or throw away a certain amount of energy. And that is E3 minus E2. That difference in the energy is thrown away. And how much is that difference? Is h times the frequency of radiation. So E3 minus E2 is emitted as a photon of energy, HF, and that is the red radiation that we see. In the picture I showed you, there was a red light there, and the frequency of that red light is given by this, E3 minus E2 equal to HFR. In that case, what is the frequency of this color? Well, that is E4 minus E2. And the frequency of the blue color is E5 minus E2. And so on. So an electron jumping from n equal to 4 to n equal to 2 will radiate the extra energy E4 minus E2. And that will be h times the frequency of the green light. That is the green light. Doesn't look green, isn't it? Similarly, an electron jumping from n equal to 5 to n equal to 2 will give out energy E5 minus E2 equal to h times the frequency of the blue radiation. Now, look at the way Bohr's model is able to explain the observation. So, any model of the atom that we put forward, it must be able to explain all these observed phenomena. There you are. Now, radiations emitted by electron transitions from higher excited state to the first excited state. Now, previously we considered electrons jumping from the third excited state to the second, the fourth excited state to the second. In other words, all these electrons were jumping into the second excited state. Now, These radiations emitted due to these kind of energy radiations, that is, all the excited electrons jumping back to the first excited state, n equal to 2. Now, these radiations are called the Bohr series. In fact, the visible light that we have all around us is the Bohr series. And the visible light is emitted when electrons jump from higher excited state to n equal to 2. All right. And the Bohr series is this that we have, I started by showing you that series. All right. Now, what happens if electrons from the higher excited state jump to the ground state? The energy level there is, the energy difference there is very high. That means the frequency of those radiations will be very high. And those radiations are the ultraviolet radiations, because ultraviolet radiations carry very high frequency. So when electron transitions end on the ground state, they produce spectral lines in the Lyman series. Well, of course, it's the scientists who experimented with it. And these are the ultraviolet radiations. So ultraviolet radiations are obtained when electrons jump from higher excited states to the ground state. So you got the Lyman and the Paschen series. Now, on the other hand, if the electron transitions end in the second excited state, from the higher excited state to the second excited state, that is called the Paschen series, and that is the infrared radiations. So look at the difference when electron transitions from higher excited state to the ground state. The energy radiations constitute what are called ultraviolet radiations. The higher transitions from higher excited state to the first excited state, n equal to 2, constitute the Bohr series or the visible light. And electron transitions from higher excited state to n equal to 3 constitute the Paschen series or the infrared radiations. Now, here I have the complete picture of all those. Lyman series, the ultraviolet radiations. Bohr series, the visible light. And Paschen series, the infrared. As we go from left to right, the frequency reduces. Now, a Bohr series for hydrogen, if you are lucky enough to see that complete series, it will look like this. You have a red, green, blue, purple, violet, and you will be able to see all those colors, which corresponds to all these transitions from higher states to the first excited state. Now, the energy difference between two levels is actually called a quantum of energy, and that quantum of energy is what we quantize as h times the frequency. And that quantum will come in different amounts depending on that frequency. So h times f, which is a quantum of energy, can have different values depending on the frequency or the color of radiation. The energy levels specified by N1, N2, N3, etc. are called the principal quantum numbers. So n equal to 1 is the principal quantum number 1, n equal to 2, n equal to 3, and so on. And so if you draw an energy level diagram, how will that look like? The lowest energy level is the ground state, n equal to 1. The higher excited state, the higher states are the excited state, n equal to 2, n equal to 3, n equal to 4, n equal to 5, and so on. So n equal to 1 is the ground state, and then you have the higher excited state. Now, the electron in a hydrogen atom will normally be in the ground state. If the atom is normal, its electron will be on the ground state. If the atom is excited, then the electron can be in any of these higher energy levels. Now remember, all our discussions are based on the hydrogen atom model. Now, higher temperature or electrical discharge, we talked about that. An external source of energy can actually give the electron extra energy, and these external sources can be higher temperature, heating, or an electrical discharge will result in an electron to jump to higher orbits or higher energy states. The energy of an electron in the ground state is negative 2.18 times 10 to the negative 18 joules. We actually calculated that earlier. So if the electron is on the ground state, that will be its energy value. And the energy of an electron in the first excited state is negative 5.44 times 10 to the negative 19 joules. And the third excited state, I have the energy all calculated. You can actually check this. You can put values in that equation and check these energy values. The energy of the electron in the ground state, the first excited state, the second excited state, and so on. Now you notice that as we go on, go higher and higher, these energy values are higher. Is that right? Can you figure it out? What is the difference between these two? What is this value minus this value? Is that a positive or a negative value? Try that on your own. Okay. Now, an electron will not stay in a higher excited state for long. We talked about that. An electron will jump from a higher excited state to a lower state by emitting a photon of energy. Now, if an electron jumps from n equal to 3 to n equal to 2, now tell me, if you remember, electron transitions from higher excited state to n equal to 2 is our visible light, isn't it? That's the Bohr series. So, what's the energy radiated when an electron jumps from n equal to 3 to n equal to 2? It will be this value minus this value. There you are. And I got this as 3.02 times 10 to the negative 19 joules. And I used red color for that because this is the energy of the red photon. Because when an electron jumps from n equal to 3 to n equal to 2, that particular transition results in the emission of the red photons. There you got the red. Now this energy is the energy of the red photon. Now I want you to find the energy of each of the other transitions. Can you do that? What is the energy of the photon when a transition takes place from n equal to 4 to n equal to 2, n equal to 5 to n equal to 2, and so on? Do that on your own. There you are. There is a green photon, a blue photon, and a purple or a violet photon. Find the energy of